Hello,
Hi, sir. How are you?
I'm good, thank you. So, any doubt from the previous topic?
No, no.
No doubt. Okay. So, last time we finished with the S block, right? Okay.
Yeah.
So, today I'm starting with the P block element. I'm sharing my screen with you. Can you see my screen? Yes, Sujay, can you hear me? Aditya?
Yes, sir.
Yeah. I can see your screen.
Right. I'm discussing about the P block. I'm talking about the periodic table that has 4 blocks. We call this is a S block. Then here we have D block, and here we have P block, and at the bottom we have F block. S block we have completed. In the S block we have group number 1 and 2 that we had done in detail. Group number 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. This is called the D block. We will do this chapter of the D block in grade 12 next year. Currently, we don't have this in our syllabus. F block also in the grade 12. In the group number 13, we have 14, 13, 14, 15, 16, 17, and 18 groups. Group number 13 and 14 are in our syllabus. This remaining are in the 12th class. Next session. Currently, we have these two groups that we need to discuss now. Group number 13 and group number 14. We'll be discussing these two groups in detail now. Group number 13.
Sorry, your voice cut out. Do you mind going to the previous page for a
Yeah.
second? Your voice also cut out. I don't know why.
Can you hear me clearly now?
Yeah, now I can.
Okay.
Now we can move on.
Okay. Group number 13 has boron, aluminum, gallium, indium, and thallium. Atomic number 5, 13, 31, 49, and 81. Electronic configuration 1s2, 2s2, 2p1. It is the neon complete 3s2, 3p1. Argon complete 4s2, 4p1. Then we have krypton complete 5s2. Here we have 3D also, 3d10. 4d10, 5p1. Xenon complete 6s2, 4f14, 5d10, and 6p1. Note it down.
Most.
So you can see that their outermost shell has NS2 NP1 electronic configuration.
Just a
General
question. What
electronic.
is this? The 49th element. Sorry.
It's a indium. INDIUM.
Yeah. Indium.
Indium.
That's right.
Now we will be discussing its general properties, atomic properties, physical properties, and then chemical properties. Boron, aluminum, gallium, indium, thallium. I'm discussing about their atomic size. You can see from this electronic configuration that as you go down the group, the number of shells increases, right? As the number of shell
Yeah. So
increases,
basically, as you go from right to left, the atomic radius increases, and as you go from what is it bottom to top or top to bottom? Uh,
you're telling wrong something.
yeah, that's what I'm.
As you
Oh,
go down the group, number of shells increases, so the size increases. As you go
yes,
down
that's right. Yeah, so it's
the
gonna be
group,
from top to bottom.
yeah.
So it'll be right to left and top to bottom.
I'm
That
not talking about right to left. I'm talking about right, top to bottom,
okay.
right?
Uh-huh.
As you go down the group, top to bottom, the atomic size normally increases. But here we have an exception case. The radius of the gallium is less than that of the aluminum. Radius of gallium is less than that of aluminum. Let us discuss why. If you see this electronic configuration here, we have entry of the D subshell here. It is not present in the aluminum. Now, important property of a D subshell is it is large and diffused. Number one, large and diffused. What is the meaning? What is the effect of the large and diffused? It is large in circumference. It is diffused. Only 10 electrons are there in the D subshell. They are quite scattered. So the nuclear charge can go out easily and pull the outer electrons inside. If the outer electrons are pulled inside, the size will decrease. That is why the gallium is smaller than that of aluminum.
Understand.
Understood. Now talk about the next
Yeah.
topic, that is the enthalpy of ionization. Aditya, can you tell
Enthalpy of
me?
ionization in
Yeah.
p block elements.
What is the enthalpy of ionization?
Just a
Energy
quick
required to
question.
remove an electron.
Energy required to eject out electron. As you go down the group, the atomic size increases. As the R increases, the attraction between the electron will decrease. Removal will become easy. And that is why, as we go down the group, this enthalpy of ionization decreases down the group.
Just have a question.
So as you go down the group, I'm not saying anything, I'm not asking you, I'm just telling you that as you go down the group, the atomic size increases, so enthalpy of ionization decreases.
Oh no, I was asking. I have a question for you.
Yeah, ask me.
So basically, what you mean by enthalpy of ionization is basically ionization energy.
Yeah,
Yeah.
ionization energy or electron, this enthalpy of ionization is the same thing.
Yeah, that's true. Actually, in school, we're doing trends in the periodic table, ionization energy, all that stuff. And yeah, just wanted to tell you that.
Yeah, ionization energy, enthalpy of ionization, or ionization potential.
Electron affinity and electronegativity.
No, they are not same.
Also,
They
those
are
two.
not same.
I know, no, I'm just saying we're doing those two as well. I'm just saying that we're also doing those in school.
Mm-hmm.
So to like those topics we're also going to be discussing right now, right? Like after this one,
Hmm. Okay. Now
which
you'll
include
understand
like
better
all.
also there also.
Yeah, that's true. That's true.
Now, next thing I'm discussing about the electronegativity. What is electronegativity? Can you tell me?
The ability to like attract electrons.
Tendency to attract shared pair of electrons towards
Yeah,
itself,
yeah,
right?
yeah. Shared pair. Yeah.
As you go down the group, the size increases, so the attraction will decrease. So the electronegativity decreases as we go down the group.
Basically, as we go down the group, the like the electronegativity decreases or increases.
Mhm.
The electronegativity increases as we go down the group.
Hmm. Yeah.
Um,
Electronegativity
I'm just
decreases down the
asking you.
group. Yeah.
Sorry.
Electronegativity decreases down the group. It means the
Okay.
tendency to attract shared pair electron decreases as we go down the group. Okay. Now we talk about next topic, that is electropositive character.
By any chance, are you going to talk about electron affinity?
We'll discuss separately. But right now we're talking about
Oh,
electropositive character.
I see.
Electropositive
Okay.
character means tendency to lose electrons. How easily the metal lose electrons. This is related with the metallic character. More easily it lose electron, more the metallic character. And now as you go down the group, what happens to the atomic size?
Increases.
Increases. Enthalpy of ionization decreases in general. That is why the tendency to lose electron will increase, and so we can say this electropositive character will increase down the group. Character increases down the group. Understood? Electropositive character increases down the group. It means tendency to lose electron increases as you go down the group.
Repeat that, sorry.
What is electropositive character? Electropositive character is a tendency to lose electron. How easily it loses electrons? So in the boron family, boron, aluminum, gallium, indium, thallium. As you go down the group, what happens to the atomic size? You answer. Increases. So the enthalpy of ionization will decrease. If the enthalpy of ionization decreases, we need less energy to eject out electrons. It means tendency to lose electrons increases. And that is why the electropositive character increases as you go down the group.
So basically, the electropositive character increases as you go down the group. Okay.
Yeah. Okay. And now next topic we can discuss is the oxidation state. We had done the chapter of the redox reaction, right? Can you tell me what is the oxidation state of boron in this compound?
Three plus.
Sir, give me a second. I'll answer it.
Yeah, you answer.
Sir, 3 plus.
Yeah, it's +3. It's +3, sir. It's +3. Oxidation state. The answer
Okay,
is
plus
+3.
3. It is because it has 3 electron outermost shell with that it can lose. You can see this electronic configuration that it has 3 electron outermost shell. They have 3 electron outermost shell that it can lose. So in most of the compound of the boron family, they show +3. they show +3. Right? But as you go down the group, if I talk about the boron, aluminum, gallium, indium, thallium, these two compound, InCl and InCl3, where it shows the +1 state and +3 state. It shows TlCl and TlCl3. It shows the +1 and +3 state. The +1 state becomes more stable as you go down the group. Now question arises here, why? Understood? Now I'll discuss here why so. Now I'll discuss here the reason why so. The reason is, if you see this electronic configuration, in case of the indium, we have a 4D subshell here and a 4F and 5D subshell here. These F subshells and D subshell, D and F subshells, these are large and diffused. These are large and diffused. So what will happen with that? They are large and they are diffused. What will happen with that? The nuclear charge can go out and pull outer ns electron pair inside. They are no more available for making any bonding. See here this electronic configuration, this 6s for 5s2 and 6s2, they are pulled inside. They are no more available for making any bond, and that is why they become inert. Understood?
Reloaded, so I couldn't hear what you were saying. Did you say anything important?
How long you went out?
Sorry, could you repeat that? Yeah, I was wondering if you could say what you said again.
Yeah, I was telling you that the +1 state become more stable as you go down the group, right? This is
Right,
because of
that's
the
right.
D and F subshell, which is large and diffused,
Mhm,
right?
mhm.
This pair of electron become
The
inert,
yeah, yeah,
right? This pair
that's
of
right.
electron become inert, and they do not take
Yeah,
part in bonding, and that is why only one electron, that is the NP, one electron is available for bonding. This is called the
yeah,
inert
that's right.
pair effect. This is called the inert pair effect. What is inert pair effect? This NS electron do not take part in bonding because they are pulled inside. They are no more
Okay.
available for
Yeah,
making
and
any bond.
also, yeah, and also 5D10 is neon, so
Yeah.
like, I mean like the
See this
top.
electronic configuration. See this electronic configuration. Here we are D and F subshell.
Yeah.
So being large
Mm-hmm.
and diffused, nuclear charge can go out and pull the outer electrons inside. They are no more available.
Okay.
They are no more available for making any bond. So this S electron become inert. They are no more available for making any bond.
Okay. Okay.
This is called
I
the
understand.
inert pair effect, and that is why only one electron is available for making bond. So we say it shows only +1, not +2 or +3.
Mm-hmm.
Now is that clear?
Yeah.
Now, next I'm talking about the boron halides BX3. It can be BF3, it can be BCl3, it can be BBr3, it can be BI3. If you find the boron atomic number is 5, I'm trying to find out its hybridization and geometry, right? Can you tell me the hybridization if possible? If you know it, let me know. Yeah. Can you tell me?
Is it sp2?
Good. sp2. So in case of sp2 hybridization, it will have a trigonal planar geometry, right? Like this. This is a sp2 hybridized orbital, and one orbital will be empty here as a 2p energy level. With this sp2 hybrid orbital, the fluorine p orbital make bonding here and form a sigma bond. Fluorine p orbital make bonding here and form sigma bond here. Right? The halogen, and the shape is trigonal planar geometry with one empty orbital in the boron here, in the p orbital here. Understood? Yes or no?
Yes, sir.
Right.
Yeah.
With this empty orbital, in this empty orbital, it can accept electron pair. For example, we have an ammonia molecule here. It can donate electron to the empty orbital. So this behave like Lewis acid, and this is a Lewis base. Lewis acid and Lewis base. Lewis acid is which accept electron pair, and Lewis base is which donate electron pair. Understood?
Yes.
So my question is, if you have BF3, BCl3, BBr3 or Bi3, all of them have the same type of structure. X means here fluorine, chlorine, or bromine. Among these, which is the strongest acid, or you have to arrange them in the increasing order of the basic character? Can you do it? Just a second. Just a second. Yes. Can you tell me? Are they equal, or what is the increasing order trending here? I want your answer.
Sir, no idea.
No idea. Okay.
Not sure.
Okay. So they
Not sure.
Aditya, this is
Not sure.
this is the structure here. Okay. In case of the boron, this is the empty orbital here, in which electron pair has to be accepted, and it is a 2p energy level. And this fluorine is having lone pair that is also the 2p energy level. So what it does is, due to the difference in the electronegativity, it takes up electron, it withdraws electron, but it makes effective back bonding. Double bond character is formed. So the emptiness here is filled here. There's no more empty. So it does not have now any more tendency to accept electron pair. It is least acidic. But here, in case of BCl3, 2p, and the chlorine has the 3p energy level. It gives back electron. If it gives back electron, but not effectively because of difference in energy, so some empty orbital is there. It can accept electron pair more easily as compared to BF3. So BCl3 is more acidic as compared to BF3. Here in case of the boron, this is of the 3p, 4p energy level. More difference, less effective. So it is now more acidic. And here we have a 2p and here we have 5p. Greater the difference in the electron and the energy level, less effective is the back bonding. And that is why, as we move from left to right, from the fluorine, chlorine, bromine, iodine, the size goes on increasing, effective back bonding decreases. And that is why the acidic character goes on increasing. Understood? Noted down?
Yes, sir.
So as we go from left to right on this scale, or whatever, then that means like, could you repeat what's going to happen?
You can see the energy gap between a 2p and 2p is very, very less. No difference. It makes effective,
Yeah.
it causes effective back bonding.
Okay. Okay.
If it causes effective back bonding, there is no any empty orbital on the boron,
Hmm.
right?
Yeah. Okay. So effective back bonding.
And yeah,
Sure.
so there's no any effect, though there's no any emptiness on the boron. That is why there's
Hmm.
no any tendency to gain electron pair. But here we have difference of
Hmm.
energy. If there's a difference of energy, the back bonding become less effective.
Okay. Yeah.
So there's some
So it actually gets less effective.
yeah,
Yeah. Go ahead.
as
Oh,
the
I was
back
just
bonding
saying.
become less effective, right?
Yeah, that's what I was saying. Just as you go from left to right, it gets less effective for back bonding.
Right. So the emptiness is created here. The
Hmm.
chlorine takes up electron by the difference of electronegativity, but does not give back. It means there is an emptiness here
Hmm.
in which electron pair can be
Hmm.
accepted, and that is why the Lewis character, basic acidic character increases here.
Hmm. Okay. 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 I understand.
In case of the aluminum chloride, AlCl3, this does not exist singly, but it exists as a dimer, and we call it the Al2Cl6. Dimer is formed. How? AlCl3 is a structure like this. Second AlCl3 is like this. It gives electron pair to the empty orbital of aluminum here. It gives electron pair. So a dimer is formed, Al2Cl6.
Al2Cl3.
Yeah, Al2Cl6 dimer is formed. Dimer
Oh,
means
oh,
two units
yeah,
are joined
six.
together.
Yes. Yes, that's right. Okay, yeah, I understand.
But BCl3 does not exist as a dimer. It exists as a monomer. Right? Reason is this boron does not have empty d orbital. But here the aluminum has empty d orbital. In those empty d orbital, the lone pair gives a back donation. Understood? Any doubt till now?
No. And also, you could visually like represent this. Like you could say boron doesn't have an empty d orbital by just writing its electron configuration, which is just 1s2, 2s1. So that's how you could also think of
Yeah,
it, can't you?
yes, yes. Now talk about the another compound that is known as a diborane. Diborane is a B2H6. Now, if you see the boron, atomic number is 5. Electronic configuration is 1s2, 2s2, and 2p1. If you see this electronic configuration, it has only one electron, and by the excitation of the electron, it can make available 3 unpaired electrons. If it makes 3 unpaired electrons here available, it means it can make maximum 3 bonds. BH3 should be formed. But practically we get B2H6. Question arises here why and how. So we'll now discuss here how so. Understood? Now I'll discuss here how this B2H6 is formed. For that, it is said that boron after excitation, it's a 1s2, 2s1, and 2p2. It undergoes sp3 hybridization. This empty orbital also take part in bonding. 1s and 2p and one empty p orbital here. 2s, 2px, 2py, and 2pz. After intermixing, we'll get here 1, 2, 3, and one empty orbital. Like in sp3, we have a tetrahedral geometry. So the boron is here with one empty orbital. All of these are sp3 hybridized orbital. But one sp3 does not have any electron.
Hi, sir. My connection actually cut out again. What did you say? Sorry, it cut out for just like 30 seconds, 20 seconds.
Okay. I just simply told that it is sp3 hybridized. So it is a tetrahedral
Mm-hmm.
geometry. And
Okay.
in this empty tetrahedral geometry, one orbital is empty. That's it.
Okay.
I think you might have done this part also.
Yeah. Yeah. Could you
Right?
go up for a second on the
Sure,
page?
sure.
Thank you. Okay. Yeah, I understand. Yeah. Yeah. It's good now.
So in the diborane, we have two such borons are there, right? One with this. Second boron, it's empty with the filled. It goes like this. sp2 with the sp2. No, sp3 with the sp3, right? But empty is here. And here also sp3 of the boron with the s orbital of hydrogen here. sp3s. Right, s orbital here, sp3 here. Form a sigma bond here. And here the one more hydrogen s orbital overlap with the empty and filled of the orbital, filled of the d orbital here, sp3. So here we have two electrons, but they are bonded with the three centers. One is the hydrogen and two boron. So we call this is a, if you connect these 3 points here, this is 3 points here, right? We call it's a 2 electron 3 center bond. 2 electron 3 center bond. One above and one below. It is like that. That is why we call it banana bond due to its shape. Just give me a second, please. Understood?
It says 2 center, 3 center bond.
Yeah. It's a 2 electron because the 2 electron, one is of the hydrogen, other is of the boron, and but 3 centers are bonded here.
Oh, done, sir.
So this boron is bonded with the 4 hydrogen here, and other 2 hydrogens are perpendicular here. These 2 hydrogens are perpendicular. We call them as a bridged hydrogen. And these hydrogens are called the terminal hydrogens. Done? This is called diborane. Understood? Till now, any doubt? I'm stopping sharing for some time. Yes, Sujay. Aditya, do you find any difficulty till now?
No, no,
No.
no.
Okay. Just give me a second. Let me open one assignment for you. Wait, please. I'm sharing my screen again. Aditya, can you see my screen now?
Yeah, now I can.
Okay. Now,
Sorry,
cassette.
sir. My connection got
No
not
issues.
I don't know, disconnected again, but I understood what you said. You just said we have to open this you're gonna
Yeah,
open an assignment for us and we have
yeah.
to do it.
So we have just opened the assignment and we're doing some questions here. Of the boron family, only we will discuss, right? Other family will not discuss. This carbon family. Leave this. Okay. We'll discuss this boric acid. First of all, we'll discuss here what is the boric acid and what is the correct answer here, right? I'm coming to this boric acid. H3BO3 is called as a boric acid. H3BO3 is boric acid. If you see its structure, it is like this. It can give H positive ion. It can give H positive ion. So I can say it can give H positive ion. So it is acidic in nature. How many H positive ion it can give?
3.
It can give 3 H positive ion, right?
Mm-hmm.
Okay. So I can say the basicity should be equal to 3. Basicity means how many H positive ion it can give. Okay.
But why are you writing that in the basis place? Because isn't there aren't you supposed to write that in the
See,
acid section because acid is H plus and base is OH minus.
yeah, I say that this is boric acid. It can give H positive ion, but how many H positive it is able to give?
3.
3. So basicity should be equal to 3, right?
Yeah, because OH minus is also 3, so
Yeah. So, but practically, this is found to be wrong. The basicity practically is found to be equal to 1 only. Means it is capable of giving only 1 H positive ion. Now, question arises here, how 1? Practically, it is showing 1, right? Now, how 1? The reason is this is the boric acid. When it dissolved in water in the empty orbital, it give electron to the boron here. It make a coordinate bond here now. Oxygen carrying positive charge is unstable. It cannot take up the positive because oxygen is electronegative element. So it gives the H positive ion from here and it forms here BOH4 negative plus H positive. Right? It gives only one H positive. Third is for the basicity is equal to 1. So
But
basicity is equal to 1.
isn't there four OH
No.
minus? Because as
See,
a
basicity means
subscript.
what the definition of the basicity? Basicity means number of H positive ions given by an acid.
Oh, okay.
So
Because
I
usually acidic means H plus and basic means
yeah
OH minus. So I was just a little confused.
yes you're right. But here the term is opposite. For the acid it's a basicity and for the
Yeah.
base it is acidity.
I'm guessing this is an exception.
Yeah. Understood? Now why does basicity is equal to 1?
Yeah.
Okay. Now next. If we see this question here. So question number 1. Check this question number 1. Boric acid is a weak monobasic acid. Monobasic means it can give H positive ion. So it's a and act as a Lewis acid. Lewis acid means which accept electron pair. Right. So I have shown you the mechanism in which it is accepting electron pair from the water. Yes or no? It acts as a Lewis acid. Lewis acid means which accept electron pair. It accepts electron pair from the water. From water. In the following set of the reactant, which set the best exhibit the amphoteric character of the aluminum hydroxide. Amphoteric means which is acidic as well as basic in nature.
Oh, sorry, sir. Could you repeat what was monobaric or mon basic? Yes, monobasic.
Monobasic means which gives only one H positive ion. Monobasic means
Okay.
this.
Yeah, got it. So basically, boric acid is a weak monobasic acid and acts as a Lewis acid
Mhm.
by accepting a lone pair of electrons. Could you describe that one more time?
If you see this one, right? When we dissolve in water, the water donate electron pair and the boric acid is accepting electron pair. It accept electron pair. When it accept electron pair, it is acting like a Lewis acid.
Yes, because Lewis acids accept
Yeah,
electron pairs and Lewis spaces donate electron
yeah.
pairs.
And it is monobasic because it is giving only one H positive ion.
That's true.
So if we come to this,
Amphoteric means acidic as well as basic.
yeah. The question is here, which of the following set shows both of this? See that set 1 shows that it is giving the OH ions, means basic. Set 3 shows it is acidic in nature. It means I can say 1 and 3 is the correct answer. Understood? Hmm.
Yes, sir.
Now, borax. First of all, I'll tell you what is this borax. Borax is Na2 B4O7 dot 10 water molecule. Na2 B4O7 dot 10 water molecule. Right? Upon heating, it forms H3BO3. What should I add so that it become H3BO3, boric acid? Just a second. We should add here HCl, hydrochloric acid. It will become boric acid. And boric acid upon heating gives B2O3. If we heat the B2O3 further with Y, what should I add to the Y so that it become boron only? I need something as a reducing agent which takes up the oxygen. So it is just a minute. Remember it is the aluminum. So why is the aluminum here? That can reduce the boron because here aluminum is more reactive as compared to the boron.
Just a quick question.
Yeah.
So aluminum is always a reducing agent.
Yes.
Oh, okay.
This borax Na2B4O7 react with HCl 5 water molecule. So the first step is this, and B2O3 just it need aluminum here. It will get converted to boron here. Understood? Next question. Number 4. Boric acid plus sodium hydroxide gives. How can this reaction made to proceed in the forward direction? By the addition of cis 1,2 diode. It's just to remember it. Right?
Sorry, sir, my connection cut out. I don't know what you
Okay.
were saying. Do you mind saying this one again?
I had said
Oh
only.
no, I understood this one.
Yeah. Just this question.
This
This question we have
yeah.
discussed only.
Mm-hmm,
How
mm-hmm.
can we make this action to go in the forward direction? You would remember this only that addition of cis 1,2 diol make the reaction possible in the forward direction. Okay.
Could you write that somewhere by any chance?
Cis 1,2 diol
Mm-hmm.
is this compound.
Yes.
When we have OH group on the both on the same side.
Okay.
Okay, group 14 we have not done, so we'll not do this part. Question number 6. The factor responsible for the weak acidic nature of the BF3. It's a weak acidic, right? It's a weak acidic. The boron trifluoride is a weak acid. Why do we say so? It is because the reason that here we have a boron that is having an empty 2p orbital here, and here the fluorine lone pair are here. They are also the 2p energy level, and effective back bonding takes place between pp. So we call it p pi back bonding. P orbital making pi bond, so we call this is a p pi back bonding. Understood? Yes or no?
Yes, sir.
Borazone and borazole. P stand for planar and stand for non-planar. This you have to remember it. This is a non-polar. This is a polar, and this is also polar. Just remember it. Understood? Boric acid is polymeric. Polymeric means many molecules are joined together because they can make hydrogen bonding. Like this. This is a boric acid. BOH. BOH. OH, B, OH. Similarly, if I make one more molecule of the boric acid here, it will make bonding like this. This is a hydrogen bonding. Understood? Similar to graphite, boron nitride is similar to the graphite. Understood? To a piece of charcoal, sulfuric acid is added. What will we get? To a piece of charcoal, carbon dioxide and sulfur dioxide gas are evolved. Just a second, just a second. Yeah. Which question? SO2 and CO2. C option, correct answer. Just note it down. Understood?
Mm-hmm.
Okay. This we have done. Just a second. Okay, till now, any doubt, ask me. Understood? Each and everything till now?
Yep.
Right. Students, just give me a minute, I'll be back. Yes, friends, I'm back now. Hello.
Hello.
Can you see my screen?
Yeah.
Okay. Now I'm discussing about the carbon family. Group number 14. Group number 14. Carbon, silicon, germanium, tin, and lead. Atomic number 6, 14, 32, 50, 82. This is the atomic number. And now if you see this electronic configuration, 1s2, 2s2, 2p2. Neon complete, 3s2, 3p2. Argon complete, 4s2. Krypton complete, 5s2, 4d10, 5p2. Xenon complete, this is the electronic configuration.
Sorry for SN. You wrote Krypton and then you wrote 5s2.
Yeah,
Sorry, just
5s2, 4d10. Okay. As you go down the group, how will the size vary now?
It will increase.
It will increase. Yeah. As you go down the group, size increases. What about the enthalpy of ionization?
It will decrease.
It will decrease. Good. Now, if I compare boron with the carbon, which will be bigger in size?
Boron.
Yeah. As you move from left to right, the size
Yeah.
decreases.
Size decreases.
Yeah. What about the
Yeah, but as you go from right to left, the atomic size increases.
yeah, as you go from left to right, ionization energy increases. Right. But as you go down the group, the size increases. Now, what about the electronegativity?
It will decrease.
Yeah, it will decrease. Yeah, electronegativity decreases. Right. Perfect. Now, what about the oxidation number? What do you think the oxidation number should be?
Sorry, my connection cut out again. What were you saying about the oxidation number?
I'm asking you, how will the oxidation number vary now? What is the oxidation number of the carbon? If I check the oxidation number of carbon here.
Carbon,
If I say
think
I
it's
have a molecule of the carbon dioxide, what is the oxidation number now?
carbon dioxide, yeah.
Yeah. Tell me, what is the oxidation number of carbon now?
+4.
+4. It has 4 electrons in the outermost shell. So it will be losing 4 electrons, and that is why the oxidation number is equal to 4 for all the elements. But for these two elements here, tin and lead, they form two types of compound. One with the +2 state, other with the +4 state. You can see PbCl2 and PbCl4. Both are possible. In the +2, it's a +2 state. Here we have a +4 state. Now, +2 state is more stable than the +4 state. Can you tell me the reason for this?
Sn and Pb have D and F subshell, and D and F subshell are large and
Yes.
they are diffused.
What do you call this phenomena? What do you call this phenomena?
Inert pair effect.
Yes, we are right. Perfectly, perfect. This pair become inert for making bonding. So it's the inert pair effect. Inert pair effect. Due to the inert pair effect, the +2 is more stable as compared to +4. Now, my question is, what type of compound the carbon will make? Will it make covalent bond or ionic bond?
Just want to tell you, ionic bond is metal plus non-metal, and covalent bond is I think it's non-metal.
Right now, definition is not important. Right, the important is what type of compound the carbon will make. Will it make
Covalent.
covalent here? Why covalent? Why not
Covalent.
ionic?
Because
carbon
if
can
it's
only
like
share 4
if the
electrons.
electronegativity number is lower than if it's like lower than 1.7, or if it's like 1.7, like basically if it's like lower than 1.7, that means it's covalent.
It is forming +4 state, right? +4 state carbon. +4 state and
Yeah.
carbon, right? +4 state and carbon means it is a very, very small size particle. It will have a small size and high polarizing power. So it will polarize the anion towards it more effectively, and that is why it will tend to form the covalent compounds because of very small size. Okay.
Mm-hmm.
Now, let's try on reducing nature. Can you tell me what is meant by the word reduction?
Gaining of electrons reduction.
Yeah, the one which gives electrons, right? So any element that can give electrons and they can lose 4 electron outermost shell, right? They have 4 electron outermost shell, so they can lose 4 electrons, and that is why they are reducing in nature. As we go down the group, right, they can give electron for the reduction. They can give electron for the reduction. The one which gives electron for the reduction is a reducing agent. Is a reducing agent, right? So as you go down the group, atomic size
Increases.
increases. Enthalpy of ionization decreases, right? So tendency to lose electrons increases, and that is why the reducing character down the group increases. As you go down the group, the reducing character increases. I hope it's very clear now. Carbon can form single bond, carbon can form double bond, carbon can form triple bond, right? But other elements do not form this type of bonds. Can you tell me the reason? What is the possible reason?
The tetravalency of carbon and catenation property.
No. In case of carbon making double bond, what is the hybridization here?
What is sp2?
sp2. When it is sp2 hybridized, the carbon is having a trigonal planar geometry, right? One orbital is perpendicular here. Other carbon are also making sp2 hybridization here, and it is now like this. So that will overlap sideways and form pi bond. It is sigma bond and pi bond. But in case of the other element which are comparatively bigger, they will have bigger size of the p orbital. In case they have a bigger size of the p orbital, they will not overlap sideways, and that is why they can't make p pi bonding. Only carbon can make p pi bonding. But other elements do not form p pi bonding. Understood? Because here we have a 2p orbital here, 2p orbital here. In other element, there will be some 2p or 3p or 4p. They're bigger in size. Their effective overlapping, side overlapping is not possible. That is why they can't make p pi bonding. Hopefully, it's all clear.
Yes, sir.
Right. Now, I'm not talking about the d pi p pi bonding. If we talk about this compound NCH3, or we talk about ammonia here. First of all, ammonia. In the ammonia molecule, what is the hybridization of the nitrogen here? Can you tell me what is the hybridization of nitrogen here?
Is it sp3?
Repeat, please.
Is it sp3 or ammonia?
It should be sp3. right? One lone
Yeah.
pair and 3 bond pairs are there. So the geometry is tetrahedral. It's a sp3 hybridized orbital, so the geometry is tetrahedral. Geometry is tetrahedral. Similarly, if I talk about this molecule, in place of the hydrogen I'm putting a methyl, it will also be tetrahedral. Same geometry, same shape. But if I talk about this molecule, SiH3 whole thrice, it is called a trisilylamine. This compound is trigonal planar. This compound is trigonal planar. Now question arises here, why it is trigonal planar? Now I'll talk about a D pi P pi bonding. Are you getting me? I'll talk about D pi P pi bonding now.
Okay.
The reason behind this is the silicon is having empty d orbital and nitrogen is having a lone pair here. This is having empty d orbital and nitrogen is capable of donating the back bonding lone pair. So nitrogen will donate electron to the silicon empty d orbital from all the three sides here. Got it now?
Mm-hmm. Yeah.
So that is why this is a square planar. It is not tetrahedral because it is capable of making the d pi p pi bonding. Silicon can make, but carbon cannot make. Now talk about reaction with oxygen. Carbon plus oxygen to give what? Carbon
Carbon
dioxide,
dioxide.
right? Silicon plus oxygen, it will give silicon dioxide. germanium dioxide, tin dioxide. This is acidic in nature. This is less acidic. And these all are amphoteric in nature. What is amphoteric? Which can act like an acid as well as a base.
Yeah.
That is called as an amphoteric. Carbon dioxide is acidic in nature.
Just a question.
Yeah,
Why is SiO2 less acidic again?
I'll come to it. When carbon dioxide reacts to the water, it forms carbonic acid, H2CO3. This carbonic acid is H2CO3. This is a compound here. And if it loses the H positive ion, you can find that the lone pair on the oxygen are in conjugation with the oxygen and they form resonance stabilized. It can give the H positive ion very easily because after losing the H positive ions, it will give the H positive ion easily and it form more stable product here. Understood? But in case of silicon dioxide, if we talk about silicon dioxide, whenever it is dissolved in water, it will form a silicic acid. And after loss of H positive ion, it is not going to be stabilized. There's no any resonance possibility here. And that is why it is less acidic.
Okay, so basically the reason it's less acidic is because it has like
After losing H positive ion, it is not getting stabilized. But
after
carbonic
losing
acid is, yeah,
H positive. But the thing is, the amount of the number of O, like the oxygen ion or oxygen, um the number of oxygens are 4 and the number of hydrogens are 4 as well. So
it doesn't matter.
like
It doesn't matter. Point is whether the loss of H positive ion makes it stable or not. If you are
okay, but
losing,
how can we tell from this diagram or just this compound that
uh,
H positive loses
see, we have
an
to. We
electron?
should know this chemistry. We should know this chemistry now, right?
Mhm. How exactly?
This is the carbonic acid
Yeah.
obtained by the carbon dioxide.
Mm-hmm.
And after when you lose the H positive ion, there is a negative charge on the oxygen, and you can see there is a possibility of resonance over here.
Okay.
That is why But in this case, if we lose the H positive ion from any one of this, it is not going to be stabilized. O is having a negative charge. It is not in resonance with the not clear. So whenever we can say carbon dioxide and we react with the sodium hydroxide is the base. It will form a Na2CO3 plus water. So you can see this is a base and this is an acid. It forms salt. Similar,
Neutralization reaction.
pardon?
Neutralization reaction.
Yeah, it is a neutralization reaction. The second reaction with the silicon dioxide, and I told you that silicon dioxide is less acidic. So here the reaction will be slow. Salt will be formed. It's a base, it's an acid, salt is formed, yes. But the rate of reaction is slow. Understood? But in case of the silicon tin, I told you that it is amphoteric in nature. It can react with base and it form here tin sodium stannate. But it also
You
react
said
with acid to form SnCl4 plus 2 water molecule. With sodium hydroxide that is a base, it is acting like an acid. HCl is an acid, so SNO2 acts like a base. It is a dual character. Dual character means it is acting like an acid as well as a base.
quick question. So you said when you were writing NaO2 or something, you said it's amphoteric. Like you said it was amphoteric or
I said with the sodium hydroxide as a base, SNO2 act like an acid. And HCl
yes.
is an acid, it is acting like a base. And that is why I say this
Oh
is amphoteric.
yes. They could be yes, amphoteric means it basically it's acidic as well as basic. Like it can adapt to its surroundings basically.
Yes.
Yeah, got it.
Understood now, right?
Yeah.
Similar reaction is shown by lead also, PbO2. That is also amphoteric. With sodium hydroxide, it forms Na2PbO3 plus water. It's a base, so it is acting like an acid.
Yeah.
Right? This, when react with an acid like HCl, it again forms salt, PbCl4 plus 2 water molecule. So this is an acid and this is a base.
Yeah.
Again, you can see it is amphoteric in nature.
Mm-hmm. Yeah, I can see that. And just a quick question. Just a basic, this little bit of a basic one, but just wanna, I just wanna like refresh my memory. So basically, 2NaOH, that two, like the coefficient, whenever we're reacting it, like putting it on the reactant side, we always have to put it as a subscript.
Yeah.
Yeah. Yeah.
Got it now? Understood?
Yeah. This is good. It's good.
Noted down?
Almost.
Okay. So the carbon
Let me see.
family will complete next time. It is a lengthy topic, right? We have
Okay.
covered the boron family completely.
Mhm.
I have stopped sharing with, right?